going to do a couple of examples. Okay, so the first one is this series. Okay, so this is what we call the Riemann series. It's also called the generalized harmonic. Okay, it's easy to see that if alpha is 1, then this is the harmonic series that we have seen. Okay, 1 over n, and we know that this is divergent. Okay, but what happens for other values of alpha? Is this convergent or divergent? Well, let's see. Okay, we're going to apply Cauchy's condensation formula. Okay, so we have a sub n, so a sub n is 1 over n to the alpha. Okay, and we need to compare it with 2 to the k a 2 to the k, so this is 2 to the k 1 over 2 to the k to the alpha, right? Okay, so this is the series from k equals 0 to infinity, 2 to the k divided by 2 to the alpha k. Okay, right? Can we see if this is convergent or not? Well, we can operate here. This is k equals 0 to infinity, and then this is 1 over 2 to the k alpha minus 1, right? But then we can apply the properties of the exponential and say this is 2 to the alpha minus 1, everything to the k, right? Okay, so now if you think about it, this is the same as saying this is k equals 0 to infinity of x to the k, where x is 1 over 2 to the alpha minus 1, right? But this is the geometric series, right? And we know that the geometric series converges where the absolute value of this x is smaller than 1. Okay. Now this is positive, so that we can operate with this. This is equal to 1 is smaller than 2 to the alpha minus 1. Okay. And if we take logarithms, we have 0 is smaller than alpha minus 1 logarithm of 2. Okay, so again, alpha minus 1 times the logarithm of 2. The logarithm of 2 is a positive number, so the only way that this thing cannot be 0 is if alpha is negative. Okay, so this implies that alpha has to be greater than 1 for this series to be convergent. Okay, so let me recapitulate here. What we have proven is that if alpha is greater than 1, then this series is convergent, the Riemann series. If alpha is smaller or equal than 1, it will be divergent, okay, just like the harmonic series, sorry, the geometric series. Okay, so that's very interesting. So you have the sum of 1 over, for instance, n squared or n cubed or something like that. Everything like that will be convergent. But if you have, for instance, the sum from n equals 1 to infinity of 1 over the square root of n, this is not convergent. This is divergent. Okay, so remember that. If alpha, this is a very important result. Okay, so you need to remember that the convergence of this series as a function of this parameter alpha. Okay, and so if because we will use them for the comparison test and for other tests that we will see later. Okay, so remember that. And okay, another example is, it's useful to, the Cauchy's condensation test is useful when you have logarithms. So for instance, this from n equals 2 to infinity of 1 over n times the logarithm of n to the alpha. Okay, so this is a sub n is 1 over n times the logarithm of n to the alpha. Okay, so again, in order to study the convergence of this, we will say from k equals 0 to infinity of 2 to the k and a, but instead of writing n here, we have 2 to the k, so we have 2 to the k, and then we have the logarithm of 2 to the k to the alpha. Okay, so then we have let's see, 2 to the k and 2 to the k cancel each other out, so then we have the sum from k equals well, in this case it has to be 1, right? Because if k equals 0, then the logarithm of 2 to the k is 1. So 2 to the k is 1, the logarithm of 1 doesn't exist, so this is from 1. Okay, k equals 1 of 1 over, and this is exactly the same as k logarithm of 2, right? So this is k to the alpha logarithm of 2 to the alpha, but we can take the logarithm of 2 to the alpha outside the sum, right? And then we have the sum from k equals 1 to infinity of 1 over k to the alpha. But this is just the generalized harmonic series, or the Riemann series that we have just seen. Okay, so this original series will be convergent, okay, if alpha is greater than 1, and divergent, sorry, not greater than infinity, equal to infinity, if alpha is smaller than equal than 1. Okay, just like before. Okay, so you can see the usefulness of this test.